Can you see the screen?
Yes, sir.
Yeah. So we have discussed the concept of duality and the other related paradigms. So, and we have also seen the economic interpretation of duality and the dual form, the meaning of the dual objective and the constraints, right? The dual variables also. And in the last class, we have also seen that how um, the dual how the dual variables help you in analyzing sensitivity in the data. So in the sense, if we change the selling price or the profits, right, or if we change the right hand side, which means the availability of the raw materials, then how do these changes affect the optimal solution and the objective value, and how the dual variables play an important role in answering these questions. We have seen all those. Okay, so now from the concept of duality and the dual theorems, which are strong duality and weak duality, we know that we are familiar with this graph. So for a particular given solution, if we apply the simplex method on the primal form, so if assuming that it is in standard form, so that means the maximization objective. So we start from the origin 0, right, where the objective value is also 0, and then we slowly improve, in the sense we increase the objective value, right? So primal feasible, so all the feasible points on this line, so we start from the bottom and then we move upwards in terms of objective value, right? And we then hit the optimal line. Similarly, if we look at the dual feasibility, that is the all dual feasible solutions, we know that it will be on the other side of the line, right? Because their corresponding primal solution would be infeasible. Okay, so if we consider the feasibility space of the dual, then it will be on the other side, and because it's a minimization problem, we will, if we apply simplex on the dual of the problem, we will start from a higher value, higher objective value, then we'll come to the, we'll lower the value, we'll find better solution, in the sense that it will lower the objective value until we hit the optimal line, where both the primal feasible solution and dual feasible solution give the same objective value, which is the optimal one, right? So we are familiar with this concept. Now the idea is that can we uh, utilize this concept to even simplify the simplex method for non-standard forms. So let us take an example. Say this one, right? So this suppose this problem is given to you, and if you look at it closely, it is nothing but the dual of the our initial problem, right, which we used to explain the simplex method very early, right? That maximization 3x1 plus 5x2 subject to 3 constraints, right? So you recall that form, right? So it is nothing but the dual of that form. But suppose it is given, we do not know, suppose this is given as the as the primal problem to us. So I have taken this example, and you are required to solve this, right? You are required to solve this problem, this LP. So what would be your approach? How would you solve this problem?
So can you repeat the question? It was not clear, like some audio
Suppose this
problem.
problem, yeah, this problem is given to you, max z subject to these two constraints and y1, y2, y3 greater than equal to 0. Suppose this problem is given to you. Now, how do you solve it by simplex? What would be your approach?
We first choose basic variables, and then we first find, then among the non-basic variable we try to find the entering variable, and
No, no,
among the
no, I'm not asking about the simplex operation. I am
okay,
saying
okay.
that, first of all, you tell me whether this is in standard form or not.
No, it's not in standard.
So which method do you apply to solve this? It is not in a standard form, right?
Yes, sir.
So which method would you apply to solve this?
Yeah, big M.
Big M
Big
or
M
two
method.
phase?
Yeah, big M.
Right.
Yeah, big M or two phase.
So
Yeah.
because you have this greater than equal to constraints, right? Now the problem with this big M and two phase is, as you can see, that you have to add additional variables and then you drive it to 0, right? So you spend some substantial amount of time in phase 1 where you try to force all these variables to 0 in order to find an initial BFS for this original problem, right, where you start the phase 2. Now, because you now know about the duality and the concepts of duality, now you should be able to do away with this two-phase method. How? So suppose I try to make it to the standard form by just multiplying it with -1, because these two are greater than equal to, right? So simply multiply it with -1. So the table becomes this one, isn't it? This is the table. If we multiply it with -1, where y4 and y5 are the slack for the equation for the constant 1 and constant 2. Clear? Is the table in standard form? If we simply
Yes, sir.
multiply -1 with
No,
the left hand side and
No,
right hand
no,
side, then we get this table, right? Is it in a standard form now or
no.
not?
no. B is negative. The constants.
The
B
RHS is negative.
RHS is negative, which means that the value of y4 basic variable is -3 and y5 is -5, right? Which is not allowed, because y4 and y5, when you define it as slack, must be greater than equal to 0. So which means by multiplying it with -1, you get this table. It's all right. It looks like a standard form, but actually it is not. It is actually giving you what? An infeasible table, infeasible solution, right? So can
Yes,
I
sir.
now say that this is in standard, this is a standard form, but an infeasible one, right? Solution is infeasible. Otherwise, there is less than equal to and max objective, all these things are satisfied, but the solution is infeasible, right? Now, what do you know? So this is a basic solution, but infeasible one. So not BFS. Now, for an infeasible basic solution, what would be its complementary dual solution? What would be the nature of its complementary dual solution?
It would be feasible.
It will be feasible,
Feasible.
right?
It will be feasible, but not optimal.
But not, may not be optimal, right? Of course, will not be optimal because the primal solution is infeasible. So we know that its dual solution will be feasible. So what this dual simplex does, instead of solving the primal problem, it attempts to use the dual solution and solve from there. So if I take its dual, suppose the dual of this given problem, we get what? We get maximization 3x1 plus 5x2 subject to three constraints and x1, x2, x3, x4, x5 greater than equal to 0. So this table gives you an initial BFS for that dual problem, right? And what is that solution? What is the dual solution you get from this table?
Coefficients in first row.
Right. So x1 value 0. So these are the values y4 and y5, right? So can you tell me what will be the value of x1, x2, x3, x4 and x5? That means the dual solution. What is the value of x1?
x1 and x2 will be 0.
Will be 0. Because we know they are associated with
The slack coefficients.
yes. And then this x3, x4, x5 would be 4, 12, 18. Right. And do you correlate it with the first solution that you would have got with that problem? We started with the origin, right? So this is basically, if you take its dual, that if you look at the dual solution associated with this table, it is indicating the origin x1, x2, 0, isn't it? Which is a feasible solution for the dual. So this given solution is infeasible, but it is giving you a feasible dual solution. Okay, and we will work on that solution. So here the simplex method is modified. It is called dual simplex method, where we work with the dual solution. Okay, now accordingly the steps are changed. You know, the methods are sort of rearranged. How? Now earlier in the simplex table we first chose the entering basic variable and then the leaving basic variable by minimum ratio test. So we chose the entering basic variable by looking at the sign, the most negative one, right? And the leaving basic variable by the minimum ratio test. Here what we do, we first choose the leaving basic variable by looking at the sign of the RHS. So it is just a mirror image of the normal simplex method. So here it is y4 is -3 and y5 is -5, right? So the most negative, we choose the most negative to leave. So -5 is the most negative. So corresponding variable y5 will leave, right? And which one will enter? Entering variable will be chosen by the minimum ratio test. And how? It will be mod of. So here also the it's a bit different. So here 0 we do not consider, of course, but we consider negative entities. So here what we do, we consider this 4 divided by 0. So for the basic variables, for the non-basic variables, we here what are the non-basic variables? y1, y2, y3. y1, y2, y3, right? So we look at the non-basic variables and do the minimum ratio. So 4 divided by 0 we do not conduct. Then 12 divided by -2, mod of this whole thing becomes 6. Then 18 divided by -2, mod of this whole thing is 9. The minimum is 6. So y2 will enter. Okay, so y5 will leave and y2 will enter. So what is the pivot element here?
y2.
-2 here. This one is the pivot, right? So you make this as the pivot element 1, and then you apply the Gaussian elimination to make this column 0, right? So you get this next table. So this is the next table you are getting, right? And you look at it very carefully that what it is giving you again. So y2 has entered, you know, y5 has left and y2 has entered the base. Okay, and then what is the solution you are getting? Z is minus 30, y4 is minus 3, and y2 is 5/2. Okay. Now, is it a feasible solution for the given problem? So we started with an infeasible solution for the given problem. The next table we are getting is again infeasible, right? Because you have minus 3 here. Y4 is minus 3, which is not allowed. So we can say the complementary dual solution will be feasible. And you actually look at the objective row, you see that all are positive or 0. So it is feasible. The dual solution is feasible. And what is the dual solution now? Earlier it was 0, 0. X1, X2 are 0, 0. Now you have moved to 0, 6. So now you can connect that, okay, yes, from 0, 0 we move to 0, 6 in that example, right? So 0, 6 is a dual feasible solution for this, but its primal feasible solution is infeasible, you know, minus 3, 5/2. Okay, y4 and y2. So we have not still got a feasible solution for the given problem. So we again iterate. The idea is you start with an infeasible solution and you try to achieve feasibility and then optimality. Okay. So earlier we did it through phase 1 of the two-phase method, where we introduced artificial variables and tried to obtain a feasible solution at the end of it. Here we do not need any artificial variable. We directly work on the dual solution and try to obtain a feasible solution for the primal eventually. Okay. So again we do the same operation, dual. This is called dual simplex operation, which is a bit different, actually a mirror image of the simplex method. So first we choose the living variable. What is living here? The most negative in the RHS, which is minus 3. This is the first one is the objective row. So, you know, we do not consider it only among the basic variables. So y4 will leave. Which one will enter? We have to perform minimum ratio test for the non-basic variables. So for y1 we'll conduct 4 divided by 0. Why it is 1? Think. Three. This is wrongly written.
Sir, we will consider the coefficients in the y4 row, right?
Which one?
We should consider the coefficients in the y4 row, right? So because y4 is like the leaving variable.
No. Y4 is the living variable you have decided. Now you have to select the entering variable. So which one will enter will be decided by the minimum ratio test. Right. Minimum ratio test on the non-basic variables. So y1 is non-basic, y1, y3 and y5. So one of them will enter the base now. Right. So y1 is 4 divided by 0, we do not do it. So y3 is 6 divided by, oh, sorry. Yes, you are right.
It should be y4 only.
Yes. Right, sorry. Yeah. Correct. Because y4 is leaving, so we have to consider this row, right? So 4 divided by minus 1, mod of that is 4, right? Similarly, 6 divided by minus 3, mod of that is 2. And 6 divided by 0. So these we do not consider. So 2 is minimum. So y3 will enter. Okay. So y4 leaves and y3 enters. So minus 3 becomes the pivot. So you have to make it 1 and the remaining 0. This is what is done by doing Gaussian elimination. In the next table, we obtain the next table. Now you see the interesting thing about the next table. What you are getting in the right hand side is 1 and 3 by 2, which means y3 and y2 are now positive, which means now this is a feasible solution to the given problem, right? Isn't it? And when you look at the dual, that means its objective row, this is also all positive or 0, right? Which means this is also a feasible. When can it happen? That the given is also feasible.
It's optimal.
It's optimal.
It's optimal.
Optimal point.
Yes. So you declare that this is the optimal table, right? So Z value is minus 36. So if you see here, this was maximization problem. So if you put mean, so it will be 36. And this is actually the dual of the max problem, which we used as an example in our earlier classes, for which we obtained 36. And you see what is the value of the dual solution? 2,6. So at 2,6 we had obtained the value 36. Is it clear? So instead of working on the primal solution, you work on the dual. You apply the simplex in a complementary manner, or we say mirror image of simplex method on the dual solution. And so what is the idea? Idea is that what is the advantage of doing it? The advantage is that when you have these non-standard forms, often it happens that identifying a initial feasible solution may take a lot of time because of the phase 1 of the two-phase method. So an easier way would be to start from an infeasible solution for which the complementary dual solution would be feasible, and then you work on the dual solution. So if you work on the dual, you try to improve the dual solution, finally you will reach the optimal, right? So here these two-phase and all these things are not needed. So you can simply work on the feasible dual solution and apply simplex on it to get to the optimal. And finally we'll reach here. So if you look at this graph, right? So instead of starting from here, so often this bottom point is difficult to find for non-standard forms. What you do, you start somewhere here, some dual feasible solution for which primal is infeasible, right? And then you come down to this optimal. This is what is being done in the dual simplex method. And the earlier one, this below this arrow, is actually the primal simplex method. Okay. Now it may happen that when you reach this stage, the final stage, where you see the right hand side are all positive, which means you have got an initial basic feasible solution, and when you check the dual solution, it may happen sometimes that some of these elements are become negative, which means that although you have found a primal feasible solution, but its dual is infeasible. Okay, which should not bother you, because now you have found an initial BFS. So you can apply now the primal simplex method on it to find the optimal solution. So this version of the dual simplex is called primal dual method. So where you first apply the dual simplex to get an initial BFS, but its objective row is not optimal yet. So then you apply the primal simplex method to get to the optimal. So this is a sequential application of dual simplex followed by primal simplex, which is known as, this whole thing is known as primal dual method, which is rare. Most of the times you actually, when you find the primal feasibility, you at the same time you get the dual feasibility, most of them, but in some cases it may happen you may not get that. Is it clear? The whole algorithm, the process is clear? That what is the difference between the normal simplex and the dual simplex? Yeah, tell me. Tell me.
It's clear.
Yeah. Okay. Now. So now you try for this example. Suppose this problem is given. Max mean z 3x1 plus 2x2 subject to these constraints. So if we convert these to a standard form, it will be max minus z, right? And then subject to these constraints. So in order to make it to a standard form, we would multiply with the first two constraints with -1, right? And the third one, we don't need to do anything because it's already less than equal to 3. It's in its standard form. So can you now work it out on your own and tell me that what is the, just try to apply this dual simplex method and tell me what is the final solution.
Sir?
Yes, tell me.
The minimum value will be 4 actually. And method also I can tell. So, 1 second. So, we can okay. So, in as you showed in the first two equations, we multiply -1, and then we can keep three slack variables x3, x4, x5, and then when we do the first iteration, there we get that. Okay, so first we'll choose x3, x4, x5 as basic variables, and x4 will have the most negative that value in RHS. So we'll choose it as leaving variable, and then we do the minimum ratio test. Through that we get x2 as entering variable. And then after that, the next table itself will be like optimal.
Next table will be optimal.
Yes, sir. After that, because all the coefficients in the like all the RHS value will now become feasible, and the first row will be like all of them will be non-negative.
Yeah.
As per my calculation.
So is it matching with these tables? You see, what is the first table?
Yeah, it's matching actually.
Yeah.
Yeah, so that's why the second after the first iteration only we are getting optimal. If you see the first row.
You are getting the optimal.
Yeah.
What
The
is
second
the
table
value is z is -4. So which
yeah.
means the minimum value of z is 4, right?
Yeah. Yeah.
Okay, good. So why it is iterating one more time here?
It shouldn't iterate like because all the row like coefficients in the first column is non-zero. Sorry, non-negative. Like ideally.
So no, but just check whether these signs are correct or not. These
Yeah,
you
I
just
got the I got the same table only actually.
no, you got the same table.
Yes, sir.
Okay. So now so this was in terms of okay, right. So now graphically, can you verify whether this is correct or not? Because this is two-dimension problem.
Yeah.
X1, X2. So this is the I think graph. You plot it graphically and check whether this solution is correct or wrong. You have written down these equations, these constants you write down, and graphically you plot and see what is the optimal solution.
Sir, I think there is a mistake in the first table. If you see, I think the second row, it will be 3 and 2, but it's written 3 and 1.
Which one?
The X3 row.
X3 row, huh?
It was 3, 2 in the constraint in the previous page, and now
Yeah.
it's 3,
Yeah.
1.
3, 2, and 3, right? 3, huh?
Yeah. Yeah. It should be -2 there.
Two. Right. So now you check what you are getting. With this change, now you check.
I already had -2 there in my table actually.
Oh, after that also you are getting the same thing.
we should get minus. We should get this only. It should stop at second table. I don't know why it is iterating to the third table. Like if you see.
So that's why you check it graphically first. You plot
Okay, graphically I'm checking. Yeah, I'm checking it. Yeah.
And see whether you are getting the same or not. I think this should be -1. This one. This should be -1, isn't it? Because you divided the x4 row by -3. Fine, to make it 1. So it becomes 2. It becomes 2, right? And then in order to make this -2 0, so you multiply it with 2 and adding it here. So you multiply these 2 with 2, so it becomes 4. Oh no, this is.
We should get one there actually.
1, yeah, 1. Right. And what about this third one?
That's correct only. 1 2 1 we'll get in RHS.
So graphically, have you plotted? Anybody else who has done this? Are you getting the same thing?
I got the same thing, sir.
So just check graphically whether this is the minimum solution or not. So this is basically 0 2. But 0 2, then 0 2, yeah. Yeah, 0 2 is a feasible solution, right?
So graphically also we are getting 4 only as the answer, like 0 2.
0 2, no?
Yeah.
No, so this slide maybe for some other
Yeah, maybe for some other.
Mistakenly, it has been inserted here. This slide may be for some other problem. Yes. Yeah, it may be for this one actually. It has been inserted earlier, I think. Okay. So now this is an example of so now you know what is dual simplex method, right? So this is the example of primal dual algorithm, right? So if you are given this problem, say, right? So now if you start first, you see that it is greater than equal to sign is there, so you multiply it with -1, so you get this table, right? -8 4 10, so it is infeasible. So you have to apply the dual simplex method first to remove infeasibility to get the feasible solution, and then you look at the objective row. Fine. Here you will see that when you remove the infeasibility, the objective row would be non-optimal. That means some negative sign would be there. So then you have to apply primal simplex. So this also you try. So when you see, then the next table you get this solution. So in the table you get RHS 4014, so all positive, right? But when you look at the objective row, -2 is there, which is negative, which means this is a feasible solution but non-optimal. So essentially what is it? It is nothing but an initial BFS for the given problem, right? So you simply apply primal simplex to solve for optimality. No issues, right?
Yes, sir.
And I think for this problem, this was the solution, 21/5. Okay, by applying primal simplex, we check. This one was max. Okay, so just apply the primal simplex and tell me what is the solution here. That was for other problem. Can you apply primal simplex and give me the optimal solution? So first you apply dual simplex, you get this table where you stop dual simplex, because dual simplex you cannot apply on feasible tables. Dual simplex can only be applied on infeasible tables, right? Here you have to apply primal simplex, treating it as the initial BFS. So what will be the optimal solution? So you do it and let me know. What is someone is messaging? Okay, I think you can do it, right? You can reach, you can compute the optimal solution. So I'm stopping here for today. So far we have seen the dual and its economic interpretation, and as also we have now seen that how you can use that, you can work on the dual solution in the simplex table, you know, and then find an initial BFS for non-standard forms. So this is a very important algorithm because it essentially eliminates the need of adding artificial variables, so thereby saving a lot of computations and saving a lot of time. So this is a very important thing, and the dual simplex basically stands on the idea that the complementary solutions will be infeasible. So if one solution is feasible, the complementary solution is infeasible, and they will be feasible only at the optimal level, when both of them would be optimal and feasible. Okay, fine. So now I'll give you some assignments to practice. So these assignments will be on revised simplex method, the duality, the sensitivity analysis, and on this complementary slackness, weak duality and strong duality, and the dual simplex method. Okay.
Sir, these slides can you upload, sir, in MS Teams?
It's uploaded.
Oh, where, sir? Can't see it actually.
In file section, class materials. If you go to the files, right? And then you go to the
Okay,
class.
yeah. It's now there. Yeah, thanks, sir.
Yeah. Okay. See you then next week. I'll upload the assignment, new assignment by tomorrow.